All right, so let's get started for today. Are there any questions before I start? You can all hear me? Yeah.
So we can hear.
Okay. So the plan for this week, I think, which is the last week, is that we're going to spend the next two classes finishing up some of the languages that are part of Hadoop, Pig and Hive in particular. And then there's been a request to talk about graph databases. So on Friday, we'll talk about Neo4j, which is the sort of go-to graph database, and discuss in particular some of the differences between a relational database and a graph database. And those differences are fairly significant, and they revolve entirely around how graph algorithms are normally run. Okay? So let me just spend a few minutes on HDFS. HDFS is basically the open source implementation of GFS. So HDFS is modeled on GFS. So much of the underlying structure of GFS is included in HDFS. So it stores metadata in what's called a name node. So this is like the master in GFS. Not exactly the same, but it's very similar. Okay. And application data is placed on what are called data nodes. And these are analogous to chunk servers. Okay. And you have replication, you have heartbeat communication, you have write leases, you have journaling, you have all of those things that are actually included in GFS. Those are also going to be in HDFS, sorry. So the MapReduce.
Excuse me?
Yep.
Sorry, quick question. What is that? What kind of node is that? Is it a name node on the very first line?
Yeah, name node. Name node
Okay.
is the master, and the data
There's a
node.
little bit of glare from the light.
Okay. Yeah.
Okay. Yeah, I can see it now. Thanks.
Okay. Yeah. Name node. So. And so MapReduce is tightly integrated into HDFS. Okay. So a file in HDFS is decomposed into blocks, which would be like chunks that are replicated throughout the cluster. And when MapReduce starts, it splits corresponding to the HDFS blocks. So you remember that splits are these independent units of parallel operation that are going to be working on some subset of the data set that you're trying to actually process. And those splits are going to be directly related to where the blocks are stored for the file in HDFS. So in essence, a split is going to be working on a block. Okay? And so optimally, if we can do it, a map worker is placed on each node where a split resides. And that allows for local processing. And little network overhead. So if possible, we place a map worker on every, I think they give my terminology right. We place a map worker on every data node where one of these blocks lives for the file that we want to process, and that corresponds to a split. So the split and the corresponding map worker are working directly on the hardware where the block, where the data is actually stored. So there's no network overhead. You're just talking directly to the local disk of the server you're on, and you're doing your processing. And that's going to be the fastest way to do things, okay? If that's not possible, then Hadoop will try to assign workers close to their splits. Okay, so why might you not be able to put a map worker on the actual server that holds the block? It might be that there are already too many map workers on that block, and so there's no available CPU to hold another map worker. So you're going to have to put your map worker somewhere else, and it's going to have to actually pull the data over the network in order to do what it wants to do. So Hadoop tries to be smart about this. So first, it will try to find a server on the server rack that contains the block and put the split there, because inter-process communication within a rack is by far the fastest network communication you're going to get. If it can't put the split on the same rack, it'll try to find a rack in the same data center and put the split there, because communication within racks in a data center is going to be much, much faster than if it has to put the split in another data center in some other physical location, and now you're talking about a much, much slower network communication. So Hadoop tries to be smart about where it sticks the split. First, try to get it on the same place where the data is located. If not, try to get it in the same rack. If you can't do that, try to get it in the same data center. And if you can't do that, then you're screwed and you have to put it wherever you put it and just live with the overhead. Okay? Dun, 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 dun. And so, as I said, each data node is restricted to a maximum number of MapReduce workers. So if you overload any one of these server data nodes, you're going to just blow it up. So it has a maximum number of MapReduce workers that it's willing to actually handle, and this is managed with what's called the task tracker. So during a heartbeat, a node informs the job tracker on the main node. That's the master. Any available MapReduce slots. So each name node, each server tells the, each data node tells the name node, tells the master, I have this many available MapReduce slots. And so this is the number of additional MapReduce jobs I can take, if any. Okay. And then the job tracker schedules MapReduce jobs. Okay. So it's the master's, the name node's job to schedule MapReduce jobs as they come in. Okay, and remember that it's trying to schedule them in this way so that it can get as fast of results as possible. So the way it does this is Hadoop maintains a first in, first out queue of jobs. And it assigns in this way. So first it does a local. So if the job at the top of the queue has data local to the node, a local MapReduce worker is assigned. So a local map worker is assigned. And remaining slots are available for scheduling. So what happens is Hadoop looks at the top of the queue, it looks at the MapReduce request at the top of the queue for the map worker, and it figures out, all right, where's your split? And if there are available map worker slots on the server that contains the split, it assigns a local job. And then if there are more splits remaining, or sorry, more available slots remaining on that server, it'll schedule them as necessary. Now, if that can't happen, then you go to remote. And what happens here is that if the job at the top of the queue does not have data local to the node, a remote worker is assigned. And scheduling stops. So you can see that in this default configuration, there's a problem. And the problem is that if you assign a remote worker and hold off scheduling until that remote worker is done, you're blocking all the other worker requests beneath you, even those that might be able to find a local slot. Okay, so that's a problem. So the default scheduler will assign a job at the top of the queue with unassigned map tasks blocking all other jobs, even those who may be able to schedule local workers. Okay, So when you've got a job that's made up of workers, what it does is it assigns a local job and then it continues. When it hits the first remote job, it waits. It basically stops until this job is done and then it continues. So all the other MapReduce jobs underneath it are just sitting there waiting for this thing to finish. And if it can do a whole bunch of local assignments, it's going to finish fast, and if it can, it's not. There have been a bunch of different suggestions for how to deal with this, and they complicate the scheduling task, but they do get better performance. I'm actually not going to talk about them in detail, but I will say that they're aware of the fact that this is a problem, and they're also looking at different implementations to try to deal with it. The other thing I'll say is that it's not just the map workers that are involved in a MapReduce task, they're also reduce workers. And in its default implementation, there's no attempt to do data locality for the reduce workers. So the reduce workers are simply assigned to available slots throughout the cluster as they're found. And they sit there waiting to receive their data, do their reduce, and then return the results back to the client. Okay. So the scheduling part of Hadoop is definitely not optimal, but it does work. It's simple, and the fact of the matter is, as long as you have enough servers and enough map worker slots in each server, you're actually going to get pretty good performance. Okay. So what you would expect to happen would happen, that smaller jobs finish very quickly, larger jobs take more time. And in essence, you're processing MapReduce jobs sequentially. And so if you get in behind somebody who's got a really big MapReduce request, then you're going to wait. Okay. And there's sort of no way around that in the default configuration. All right. So any questions about that? The purpose of the scheduler is not to be complicated, it's to be simple, but not optimal, I think is how I would describe it. You know, and some attempt is made for data locality for the map workers, but not for the reduce workers. Okay, so let me talk about Pig and Hive. Pig and Hive are two languages that Hadoop provides to help you ease the burden of producing these MapReduce jobs. So Pig, I guess I should put it up here. This is a combination of Hadoop and what's called the Pig Latin scripting language. Now, Pig's particular speciality is it's meant to serve as a platform for analyzing large data sets. So Pig and Pig Latin were developed by Yahoo in 2007. Okay. And they're actually used by Yahoo, not exclusively, but they are definitely used by Yahoo. Okay. So what happens is that designers write data manipulation and analysis operations using Pig Latin. So they write directly in Pig Latin, and then a compiler converts that code into a sequence of MapReduce operations. Okay, so you don't have to write the MapReduce operations yourself directly. You can write operations in Pig Latin, which has constraints to try to guarantee that MapReduce is going to give you some benefit. And then the compiler reduces down your Pig Latin into MapReduce, a sequence of MapReduce operations. So the goals of Pig Latin when they wrote it were, one is simplicity. So this allows programmers to use a high-level language which is simple to develop and maintain, just like any high-level language. Optimization. So complex data tasks are sort of automatically, quote-unquote, parallelized into MapReduce operations. Now, we have to be careful a little bit about this because, yes, it automatically parallelizes things into MapReduce operations. But if you write code that's not amenable to that, it will run as a MapReduce job, but it's not necessarily going to be faster. And so you do have to take some care when you're actually programming to try to program in a way that's designed to help the compiler build good MapReduce sequences. And then it's extensible. So extensibility was the third goal. Developers can implement their own functions to perform any special purpose processing. Or explicit optimization. So what this really means is that if you have a very complicated analysis task, you can help the compiler by providing some additional functionality to support some of the MapReduce parallelization that you know the compiler is going to try to do for you. Okay? So let me show you an example. I mean, this is all blah, blah, blah. Let me actually show you how Pig works on a simple case. So we're going to look at a simple example. We're going to load movies.csv containing movie information. So, okay. And in Pig, you do this with the Pig with the load command. So hilariously, Pig's command prompt is grunt. And so you would say something like movies equals load, and then the arguments you give it, actually there's no parentheses. So you load movies.csv using what's called a pig store. Oops. Which got meshed in it. Pig store. And I'm pretty sure this comma just tells it that that's the delimiter between the elements. And then you say as, and then you specify what's actually in there. So you would say id : int name, colon, char array, year, colon, int, and then duration, colon, int. So what you're saying is there are 4 columns in the CSV file. There's an ID, a name, a year, and a duration, and you specify the types for each of the 4. Integers for ID, year, and duration, and then character string for name. Okay? So you can check the results with the dump command. So if you said something like at the grunt prompt, dump movies. Oh, sorry, semicolons at the end of these. Then what it would do is it would put out something like 1 comma, The Nightmare Before Christmas. Comma 1993, comma 4568, and then it might put out a 2, The Mummy, comma 1932, the original, comma 4388, and then so on down to the last one, like 49,590. K plus 8. Oops. Man, I've seen this so many times, but I forgot how to spell it. Don't judge, you've seen it too. Season 1. 2010. No duration provided. Okay? So it's just a scripting language. It allows you to load stuff, it allows you to look at stuff, and it allows you to apply operations on it that are going to be converted into MapReduce jobs. So before I go on to that, any questions? You want a synopsis of the K plus 8? When you have nephews and nieces, you too will watch movies that you thought you would never watch in your entire life. And you will not watch them once. You will watch them many, 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 many times, because young children love to watch the same thing over and over and over again. And you pray very hard that what they watch is not horrible. Okay? So importantly, oh, I'm old, I can't bend over like that. What's the matter with you? Importantly, Pig does not run any MapReduce when load occurs. Okay, so all it does is it basically loads the data, but it doesn't actually load anything. Okay, it simply remembers that you've asked to load the data. It sort of figures out some stuff about where the data is, but nothing gets loaded. It's only when dump is issued that a MapReduce operation is constructed and executed. Okay. So dump actually caused a MapReduce operation. Of course, because if you think about it, dump is just asking for the contents of this massive file, and it's spread all over the cluster in blocks. And so it's very easy to create a MapReduce job that basically powers up a bunch of splits. They all go out in parallel, grab the chunks of the information, jam it back to this reduce job, which apparently sorted it by ID and then return it. So you're going to get a result that's a bajillion times faster, hopefully, than if you just actually went onto a single file and loaded it sequentially in little pieces because it doesn't fit in main memory and spat it out. Okay. But nothing happens when you say load. It waits until you start executing operations before it starts constructing MapReduce jobs, because it doesn't know what a good MapReduce job would be until you actually execute a command. So deferring the MapReduce until you ask to expose results allows for validation and other types of checking. Prior to execution over a potentially very large data set. So an example would be that if we said dump movies list.csv, it wouldn't do anything. It would just come back and say that that's not something that we loaded for you. Okay. Even if movies list.csv actually lived out on the server somewhere. Okay. So in addition to your standard int, float, char array, other things like that, Pig does support a few other things, built-in data types. So Pig supports tuple, which if you programmed in Python, you'll know what it is. Bag and map. So tuple is an ordered list of fields. So something like this, 4, 9, 5, 8, 9, k plus 8. Uh, 2010, nothing. So you can have blanks in a tuple. Normally the difference between, you might wonder, what's the difference between a tuple and an array or a list? There's some implicit semantics to each of these fields, okay? And so the idea is that these all mean something, and if you look at it, you can probably figure out what they mean. So it's much closer to sort of the rows in a CSV file than it would be just an arbitrary data that's stored in some order. And so they're very similar, but that's the basic difference between a tuple and an array or a list. And then a bag is a set of tuples. Okay. And a map is a dict-like you have key and then you have hash value collection. Where char array keys are joined by this hash to values. So you can have something like this: name, hash, the mummy. Year, hash, 1935. And so this creates a constant with two key value pairs. Okay? And the keys always have to be strings. They always have to be char array. But the values can be whatever. Okay? And so the kinds of operations that are built into Pig Latin are very similar to SQL. So what this means is that if you know SQL, if you know SQL, you're actually going to be pretty good at Pig Latin because you've already got a pretty good idea about the kinds of things that you want to do. And you remember that I said that Pig Latin tends to constrain you to things that are going to be fairly straightforward to MapReduce into some automatic parallelization. And so SQL type commands are a good candidate for that. So you can do things like this. So in grunt, I could say something like old movie equals filter movies, that's the CSV I loaded, by year greater than 1900 and year less than 1960. Okay? And so you can see that what I'm doing is I'm just asking to pull out all the movies that are between the years, well, they'd be years 1901 to 1959 in this example. And you can imagine if you think about it, yeah, that would be really easy for MapReduce to do. That's embarrassingly parallelizable. But the nice thing is that you enter this SQL-like command. You don't have to deal with any of the MapReduce programming. That's all done for you in the background, and then you'll get an answer back, hopefully really quickly. Okay? You can do things like, you can say movie year equals group old movie by year. So this is a sorting type command, a grouping type command, and so that will happen very quickly. And then you might say something like count year equals for each movie year. Remember, these are grouped by year, so there's going to be a group for every year from 1901 to 1959. So for each movie year, generate a group and a count of old movie. And then finally, when we're done with all of that, we could ask to dump count year. And what we should see is something like this. It would say 1913, 3, 1914, 20, 1959, 87. So what you've actually done is assign a sort of selector, a filter, a grouping, and then a counter, a sorter and a counter to figure out, okay, well, how many movies for each year are there in this movie set that I loaded? And all of this would be run, each command would be compiled and run as a MapReduce job. And presumably would run much more quickly than it would on a typical SQL database. Okay. So, any questions about this? Really, you have to go in there and program in it if you want to learn how it works, but it's actually not that hard. And Given your sort of programming background, you would have no trouble picking this up and running with it very quickly. So it's SQL-like, but it's not SQL. And so you might wonder, well, what's the difference between SQL and Pig Latin? And so that question came up all the time. So I think the guy who wrote this stuff, Alan, last name, Alan Gates. He's the architect of Pig Latin. Compared it to SQL. Okay. Just to sort of give some ideas about well, what are the differences. First, it's procedural. Okay, so Pig Latin is procedural. SQL is declarative. Okay. There's checkpoints. Pig Latin allows developers to checkpoint data in the pipeline. So as you're executing the various commands, you can put in checkpoints to make sure things are happening the way you expect them to. There's control. So Pig Latin allows developers to choose operator optimizations or operator implementations. Rather than relying on the optimizer. So what this means is that if you realize, okay, for this particular operation, there's a certain way to run it, and the optimizer is not going to figure that out properly, you can tell the optimizer exactly how you should run it. So you can override what the optimizer would do by default. And of course, in SQL, no hope of that. Relationships. So Pig Latin supports splits in the pipeline. So you can have DAG relationships, directed acyclic graph relationships. Normally in SQL you only get tree relationships. And then finally it's extensible. So you can, I'm not going to write this out, but you can basically write additional code into the pipeline. And by pipeline, what he's talking about is a typical SQL command like a join or a select or something like that. Okay. So I think the point he was trying to make was that Pig Latin and SQL can do much of the same thing, but you have more control in Pig Latin so that if you want to, you can do it better. You can override what the default query engine is going to provide for you, or the default compiler is going to provide for you. Okay. Yeah. So it's SQL-like, so that someone who knows SQL won't have trouble learning how to program in Pig Latin. But the way it's actually working is quite different than SQL. Okay. So, any questions about that? Just looking here to see. So you might wonder, so what's the real purpose of Pig Latin? Like, where are we going to be using that? And the answer to that is that you're normally going to be using Pig Latin to do pre-processing on data to get it into some format that you want for further analysis. And that is a super common kind of operation. So if you think about Python, for example, when we teach Python and data analytics, data science, really Python is meant to be that bridge between the raw data and getting it into a format so that you can do analysis on it. So cleaning, error correcting, transforming, generating new fields based on the raw data that's coming in. All of the things that you would want to do to get a very clean data set so that you can then hand it off to something like SAS Viya or R or one of these other statistical analytics languages. And then they don't need to do any of that. They can just take the data, assume that it's in a good format, and off they go. Okay. In fact, I was just in my office writing some Python because these asshats who gave us this data set decided it would be a good idea to completely change the format yesterday. And so, of course, nothing works anymore. So I'm trying to figure out WTF, like, what did you guys do? And yeah, but that's my problem, not your problem. So, any questions about that? So that's one of the languages that's supported is Pig Latin, and that's usually the first language that you're going to use to process your data. You're going to create a data warehouse, like I said, a clean data set storage out of this. And then Hive is going to be the next language that you apply to that. We'll talk about that tomorrow. And interestingly, Hive really is sort of SQL. Basically, it's a relational database management system commands that you can execute, but execute within Hadoop as opposed to execute within Oracle or execute within Microsoft SQL Server or something like that. Okay, so SQL isn't gone. It just isn't completely here yet. So, any questions about any of the things that we've talked about today? Okay, don't forget that your assignment is due on the 22nd, assignment 3, and then assignment 4 is due on the 27th, I believe. Okay, and that should all be set up inside Moodle. Cornelia has been busy telling me how bored she is, so I'm going to tell her, good news, assignment 3 is ready for you to mark, and we'll see if she gets that done or not. But I assume it'll get done very quickly. So, any other questions about anything at all? All right, I think we're done for the day. Thank you very much.
Thank you.
Thanks.